hopefully you pick back up on it. So again, it's going to start repeating itself. I
I
hope.
have one more question.
Yes, ma'am. Oh, you're on record, okay? I just want you to know.
Yeah, for the calculator, like when you're making the histogram, I just don't think it looks right.
I got to change the windows. I don't know what I was thinking yesterday. I didn't even, I got one today. I'm going to show you. So I'm going to
Okay,
make up for it.
like how to fix it.
Yeah, I'm going to
Okay.
show you. I screwed up yesterday. And I don't know why I couldn't think of it because I do it all the time in Math 1. So I don't know what was going on. That's why I said I was mad because I knew what I was doing. All right. So standard deviation and variance of a discrete random variable. We're going to start there. And again, some of this stuff is going to repeat itself. Some of it's going to be kind of long to write, but it's not, there's nothing like calculation wise that's hard today. All right. So with the mean as our measure of center for a discrete random variable, it shouldn't surprise you that we'll use the standard deviation as our measure of spread. So remember we talked about this yesterday. If it's a normal curve or if it's symmetric, you're going to use mean and standard deviation. If it's not, then you're going to use median and either range or IQR. Okay. The definition of the variance. You guys remember variance? Yes, no, maybe? How do we find variance? Square the standard deviation. To find the standard deviation, we take the square root of the variance. So we already know that. All coming into play again. Okay, so we're doing the same thing. So the only difference is we only had an L1. So if I put it in terms of one bar stats, we only had an L1, and now we're going to have an L1 and an L2 because all of the L1s have a different probability. Does that make sense? So everything is exactly the same. All right, the definition of the variance of a random variable. And remember, a variance was the standard deviation squared. It's similar to the definition of the variance for a set of quantitative data. So again, that's what I just talked about. That is, the variance is an average of the squared deviation. And remember, the deviation is how far the observation is from the mean. So again, observation minus the mean, and then you square it. Of the values of the variable x for the mean mu. As with the mean, the average we use is a weighted average. So that's the difference now. Before, again, we just had the one line in the chart that we put in. Now we're going to have a weighted average. That means everything has different percentages. Each outcome is weighted by its probability. To take account of outcomes that are not equally likely. To get the standard deviation, and I'm going to abbreviate that, standard deviation of a random variable, we take the square root of the variance, just like before. Okay, so before I flip, I want to go back and remind you how to find your mean, because we're going to do that again in a minute. And I said, there's a better way. There is a better way, but this is how you do it by hand. You multiply these two, add it, multiply these two, add, multiply these two, add, so on and so forth. So that's how you find the mean. So to find the standard deviation and the variance, that's what we're going to talk about next. So if you have your chart, your value and your probability chart, your value was like x1, x2, x3, and your probability was p1, p2, p3. So what we did yesterday, that chart, mu of x is the mean of x. Then the variance of x is, this is the crappiest formula in the world. Remember, there's a different way to do it. I just want to show you by hand first. So variance of x or the standard deviation squared is when you take the observation, so x sub I minus the mean, and you square it. So that's the old formula that we had. But now we have a probability attached to it. So we have to put it down there. Now, since we have multiple, you're going to do the sum of that. So it's a summation of that stuff. And we're going to do an example. I'm not going to write it all the way out towards the bottom of this paper. I'm not going to write it all the way out, but I'll show you how to put it into that formula. So then to find the standard deviation, of x, which looks like this, it's the square root of the variance. So the standard deviation of x is the square root of the sum of the observation minus the mean squared times the probability. So the standard deviation of a random variable x is a measure of how the values, is what that should say, of the variable typically vary from the mean, which is mu of x. So think about that when we had to interpret the standard deviation. It typically varied from the mean, the amount of the standard deviation. So we're going right back to everything. I told you it repeats. We're going right back to everything that we've done before. So let's compute the variance and standard deviation. Of a familiar discrete random variable. And I don't know why there's so much space, but there's nothing that goes in that space. I apologize for that. So we're dropping down to APGAR scores. So in the last example, we calculated the mean APGAR score of a randomly chosen newborn. That's what I just showed you before we flipped over. When we did all that work, we found out the mean was 8.128. So that was the last page at the very top. That was the last thing that we did yesterday. All right, so I'm not going to write this all out because it's ridiculous because there's 10 of them. If there were 4, they may make you do it by hand, but they're not going to give you 10. They might give you 4, something like that. So really easy, but when you have 10, it takes forever. So here's what we're going to find. We're going to find the variance first. To find the variance by hand, you do the observation, which is your value, 0, minus your mean, squared, times your probability. And then you add it to the next one. So what would the next one be? Times 0.006. The next one would be 2 minus 8.128 squared times 0.007. And you keep doing that. And again, I'm not going to make you keep doing that. And then you have to put it in your calculator. Does everybody understand what I'm saying? It's just a lot of work. So we're not going to do it in our calculator. But like I said, on your test or on your homework, they may give you like 4 and say, show your work. You're going to have to do it, okay? If they ask you to do it on your test, you have to do it. So then to let you know, when I actually calculate all of that up, I get 2.066, but this is the variance. It asks me to compute. First is compute, and second to interpret the standard deviation. So now how do I find the standard deviation? When we get that, it is 1.437, which is your standard deviation. Okay, going back to that interpret. A randomly selected baby's APGAR score will typically differ from the mean by about 1.4 units. This is the same interpret that we had weeks ago. Okay, it's the same thing. Do you need to know how to interpret? Yes, you do. All right, so what's really, really cool is you can do this in the calculator. And Rachel, this is where we're going to talk about that histogram. So you can use your calculator to graph the probability distribution of a discrete random variable and then calculate the measure of center and spread. So the first thing you're going to do, and I made this really short and sweet. So there's a lot that's supposed to be there, but I made it super short because you guys can handle it. So create lists. That'll be L1 and L2. For your histogram, do a window adjustment. That's where I screwed up, Rachel. For it to fit. And then the third thing that you're going to do is your 1-bar stats. All right, so this check your understanding. I'm going to write it by hand and we're going to do it in the calculator. Sorry, my eyes itching. All right. So I'm going to read it. I'm not moving anywhere if y'all are still writing. A large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows: 0, 1, 2, 4, 0.3, 0.4, 0.2, 0.1. Compute and interpret the mean of X, and then compute and interpret the standard deviation of X. So how did we do the mean by hand? So we would do 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2. And this one wouldn't be terrible, okay? So to give this one on the test for you to do by hand would not be terrible. Okay, put that in your calculator. We don't have to do the 0 if you don't want to. I'm gonna go ahead and put it all in there anyway. 0 times 0.3, 1 times 0.4, 2 times 0.2, and 4 times 0.1. And we get 1.2. Is everybody okay with that? All right, so that's by hand. I'm going to hang on to the interpret for a minute. I'm going to go down to number 2, and I'm going to do the standard deviation by hand. To be able to do the standard deviation by hand, what do I have to do first?
Find the variance.
Find the variance first. So we're finding the variance of X first. So I found my mean was 1.2. So it's your observation 0 minus your mean 1.2 squared times your probability. Again, your observation 1 minus your mean 1.2 squared times your probability, which was 0.4. Observation minus your mean squared times your probability. I'm going to write it at the bottom. Observation is 4 minus your mean squared times your probability, 0.1. Again, it probably takes longer to put it in the calculator like this than anything else. So 0 minus 1.2 squared times 0.3. 1 minus, y'all tell me if y'all see me do anything weird, squared times 0.4 plus 2 minus 1.2 squared times 0.2, 4 minus 1.2 squared times 0.1. So this gives us 1.36 And then what do I do to find the standard deviation? So square root your answer and you get 1.166. So there's your mean and standard deviation by hand. Now I'll show you how to do it in your calculator. Go to your stat and your edit. Again, make sure your modes are on. Well, I don't want to take this out yet. That's at large scores. I don't want to take them out yet. All right. Stat diagnostics are on. Edit. 0, 1, 2, 4. And then 0.3, 0.4, 0.2, 0.1. All right. Where do we go to do our 1-bar stats?
Stat calc.
And there's our 1-bar stats. And see how now we have L1 and our frequency list is L2. If yours is not, make it L2, and L2 is second 2. There it is. You guys see your standard deviation? If they ask you to find your variance, how would you find your variance? Square that number. So you don't have to do any real work. So there they are. Any questions about how you find them in your calculator? You guys good? So I'm not going to write that down because we've already found it by hand, but I want it to be there. All right. So then let's go back and do the interpret part. So don't forget this part. So here's the difference in the mean. You have to include these two words. I know that sounds so dumb. If many, many Fridays are randomly selected. The average number of cars sold is 1.2. All right. So in context of the problem, for the standard deviation, the number of cars sold on any randomly selected Friday will differ from the mean by 1.1, you can say 1.17 cars. That's it. All right. So I'm going to go back real fast. 10. And I'm going to try to, this APGAR score one that you guys, I was showing you the histogram on yesterday and I couldn't get it right. All right. So in my stat, my L1 or my X's are from 0 to 10. So in my window, I want to make sure that my X's, our minimum is 0, my X is 10. And we can go by whatever we want to. It doesn't really matter. You can go by ones. Since we go by ones in our table, I would go by ones on my X scale. And let's see if that helps it. Okay. For your Y's, I would do 0 to 1 because we didn't have any values other than 1. And again, it doesn't matter what scale you go by. I don't care. So let's see. Let's do it. This may be really weird. I don't know. I'm just trying to change a scale. Okay. So then in my Y equals, my plot is on. And if I graph it, it looks a lot better than yesterday, Rachel.
Okay, thank you.
Does that make sense now? So all you have to do is change the window. And again, from the window, that's from your table. So like on this one that I just did. So if I'm going to graph this one, and turn this plot off. I'm going to change my window to what? What are my X's? 0 to 4. And you can go one above if you want to make it a little bit easier, or you can do it exactly what it is. 0 to 4. We're going by ones, leave it alone. Our Y min is going to be 0 because we don't go any lower than 0. And our maximum right now is 0.4. So you may just want to do it as 0.5. It does not matter. Has everybody got it? And then when we graph it, no, let me turn on the right plot. It's driving me insane. 0 to 4, 1, sorry, my Y scale, 0.1s. This is your Y's on the bottom, so my scale is going by pretty much 0.1s. And then why does it look weird? Tell me what I'm doing wrong. Do I have what I need in? Yeah. Y'all tell me what I'm doing wrong if I'm screwing it up. Nope, nobody knows. Let's try Y min 0.5. Next scale 1, but it should be okay. Let's do 1 and go by 0.1. So let's see what happens there. I don't know why it's doing such weird stuff. It's my Y scale. Whatever's wrong with my Y scale. It should not look like that. I don't know. I'll have to look at, that's the same thing that was going weird yesterday. So I'm not sure. Y min is 0. Y max is 0.5. I don't know if it's something weird at the bottom. Change X is 1. I don't know. I'll look at it again. Y'all, I at least got the other one to work right. I at least got the other one. All right, flip it over. I'll work on it in a minute. All right, continuous random variables. When we use the table of random digits to select a digit between 0 and 9, the result is a discrete random variable. So the discrete is what we've been working for. So APGAR scores were 0, 1, 2, 3. You couldn't get like a 0.5 APGAR score. Does that make sense? So they're completely discrete, which means they don't continue at all. So now what if we want a number between 0 and 1? Or what if we wanted a number between 3 and 4? So 3.5 is what we were looking for. So that's what it's talking about now, is those decimals. So when we use a table of random digits, there's discrete random variables. The probability model assigns the probability of 1/10 to each of the 10 possible values of X. That desk right there. Sorry, thank you. Appreciate it. All right. Suppose we want to choose a number at random between 0 and 1, allowing any number between 0 and 1. So again, on discrete, it would be 0, 1, 2, 3 integers. It would be integers. Now we're not looking at integers. So we want this as our outcome. Anything between 0 and 1, like 0.84522 or 0.11119. Calculator and computer random number generators will do this. The sample space of this chance process is an entire interval of numbers. So your S, we talked about S represented sample space. are all numbers between 0 and 1. So call the outcome of the random number generator Y for short. How can we find probabilities of events like the probability that 0.3 is less than or equal to Y, less than or equal to 0.7. As in the case of selecting a random digit, we would like all possible outcomes to be equally likely. But we cannot assign probabilities to each individual value of Y and then add them because there are infinitely many possible values. So in situations like this, we use a different way of assigning probabilities directly to events. And we're going to go back to those density curves as areas under the density curve. This kind of sounds complicated because you guys didn't really like the density curves, but it's just using the density curve as a visual for you to understand, okay? And we've already worked with density curves. So remember that a density curve has an area exactly 1 underneath it, corresponding to the total probability of 1. So if we look at this density curve, the random number generator will spread its output uniformly across the entire interval from 0 to 1, as we allow it to generate a long sequence of random numbers. The results of many trials are represented by the density curve of a uniform distribution. So it made everything equally likely, is what it did. So the density curve has a height of 1. It shows you that right here over the entire interval from 0 to 1 right here. So remember our area of our density curve, length times width, because it's a rectangle or a square. Length is 1, height is 1, times 1 is 1. So length times width is 1. The area under the density curve is 1. That's what I just showed you. And the probability of any event is the area under the density curve, and above, it should say the event in question. So what is, I'm going to write more underneath this so don't go anywhere, the probability of 0.3 less than or equal to Y less than or equal to 0.7. So it wants that shaded in square. So it's the area, or that rectangle, the area of the shaded in rectangle. So how long is the rectangle? What is the width? 0.4. What's the height? 1. So we do 1 times 0.4, which is 0.4. That's your probability of getting between a 3.3 and a 0.7. That's using the density curve. There are other ways to do this. Okay, other ways to do this, and we'll do it in a minute. All right, I'm gonna flip it. Right there. This figure also shows the probability distribution of the random variable Y equal to the random number between 0 and 1. Sorry. We call Y a continuous random variable. Because its values are not isolated numbers, but rather an entire interval of numbers. So what is it again? A continuous random variable X takes all values in an interval of numbers. The probability distribution of X is described by a density curve. The probability of any event is the area under the density curve and above the values of X that make up the event. So that's what we just did. The probability distribution for a CRV assigns probabilities to intervals of outcomes. Rather than to individual outcomes. In fact, all continuous probability models assign probability 0 to every individual outcome. Only intervals of values have random number generator, have positive probability. I was reading below it. To see that this is true, consider a specific outcome from the random number generator of the previous example, such as the probability that y is equal to 0.7. The probability of this event is the area under the density curve that's above the 0.7 with lots of zeros on the horizontal axis. But this vertical segment has no width, so the area is 0. So I know that sounds confusing, but it's really not if you think about it. I'm gonna slide this up so you can see a picture real fast. So we had our density curve just a minute ago, and it's 0 to 1, and its height is 1. If we're talking about 0.7, and we're trying to find the area of that line, we have a height, but we don't have a width. So we have a height, y'all don't have to write this, a height of 1, but this line has no width because it doesn't go from 0.7 to 0.8. It's just 0.7. So that's what causes it to be 1 times 0 is 0. So I just wanted to explain that a little bit more because it might be a little bit confusing. All right. We can use any density curve to assign probabilities. The density curves that are most familiar to us are the normal curves of chapter 2. We learned how to find areas in any normal distribution on page 118. Normal distributions can be probability distributions, as well as models for data. And that space that I skipped was just doing this right here. Got 4 minutes. Almost done. All right. Normal probability distributions. The heights of young women closely follow the normal distribution with mean a mu of 64 and a standard deviation of 2.7. This is a distribution for a large set of data. Now choose one young woman at random, call her height Y. If we repeat the random choice very many times, the distribution of values of Y is the same normal distribution that describes the height of all young women. Find the probability if the chosen woman is between 68 and 70 inches tall. So the question that we're trying to ask is, what's the probability that a randomly chosen woman has a height between 68 and 70 inches? All right, so I'm gonna stop here and I'm gonna go out and come back in. It's this page and that little paragraph at the top. So this is a really pretty long, we'll be done by 3, okay? We'll be done by 3, but it's a longer question. So I don't wanna break it up in the middle. So I'm gonna stop sharing, stop recording.